So for circulation integrals, we had a macroscopic measurement of circulation, which was the integral of the dot product of the vector field with the velocity vector. We had a microscopic measurement of circulation density, which was the scalar cross product of the derivative operator with my function. And we had a theorem that relates those two things together that we call Green's theorem. Right? That the circulation, the macroscopic circulation, is the double integral of the microscopic circulation density on the region inside of my curve. And so this was Green's theorem. This was the big finish of our material that we looked at last week. And now we've discovered a similar relationship between the total flux, a macroscopic measurement of flux, and the microscopic measurement of flux density. Now there's one thing we have to modify on this. The total flux should be the scalar cross product of our vector field with a unit vector in the direction of my parameterized curve, because flux shouldn't depend on how we parameterize the curve, whereas circulation did. So the total flux is going to be this scalar cross product. The flux density is going to be this dot product of the derivative with the vector field. And so what we want is we want a Green's theorem-like result here that can tell me the total flux through a closed curve using the flux density. So what would Green's theorem look like if we were to apply it to this situation? So I'm just inviting you in this last part of this exercise to speculate on what this formula should actually look like and how it should read. Once we have that formula in place, that formula is going to be our theorem. We're going to apply that theorem to a few integrals to wrap things up today. So here is your conjecture, that the flux through a closed curve, the outward flux of a closed curve, a vector field on a closed curve in the plane, is on the one hand, it's equal to the integral along that curve. So it's really like a path integral, except that instead of a dot product, we're taking a scalar cross product of f with a unit vector in the direction of the travel. But on the other hand, this should also be the same thing as a double integral of this flux density, the flux density function, which is the dot product of the gradient with f. And yeah, that's our theorem. And so from this theorem, we get, first of all, an important result called the divergence theorem. It's a measurement of how much a vector field diverges within a given enclosed region in the plane. And we also get a name for this flux density. We call that flux density derivative the divergence of a vector field. So the divergence of a vector field is this density function, del dot f, that gets used in the divergence theorem result. And so once again, just like with Green's theorem, this divergence theorem gives us a way of trading out a flux integral on a closed loop inside of the xy plane with a double integral over the region bounded by that loop.